Hello everyone, this is Professor Pankaj Biswas. I am now in live. If you have any queries, you can ask me questions. Do you have any queries? If you have any queries, you can ask me questions. Yeah. So in previous Google form, what I observed that one student asked me a questions related to what it's called metal transfer. He asked me a question, sir, how the metal transfer generally varied uh, based on what it's called voltage changes as well as current changes. One of the students asked this question. So here, just I want to clarify these things. All of you are very well familiar about metal transfer. You observe that in case of consumable types of electrode, especially in MIG welding, what I have already discussed that okay, metal transfer generally grouped into two main categories. One is called free flight metal transfer. Another one is called means contact types of metal or short circuiting types of metal transfer. Apart from some other categories of metal transfer also are there. Another one is called slug protected metal transfer. Some other form of free flight transfer also I have discussed, that is called repelled form metal transfers, pulse mode metal transfer. So you observe that in case of consumable types of material, generally metal transfer is taken place from consumable electrode to workpiece. That you observe that. Here what happens generally due to this current and voltage, that means welding current and welding voltage, you can say the heat is generated on the electrode. Due to this heat, generally you can say this electrode is going to melt and droplet start forming. After that, in droplet region, there occurs some what it's called different types of forces. I have already discussed these categories of forces also. This force generally you can say in metal droplet region, whatever the different forces acting, this forces also grouped into two different categories. One is called aid force, another one is called retarding types of force. Aid force also you are very well familiar. One aid force means which the force which support the you can say transferring the metal droplet from electrode to workpiece. That types of force is generally known as aid force. One of the most important aid force I have already discussed, that is called Lorentz force. So due to this Lorentz force, generally which you can say neck formation is taken place, and due to this neck formation you can say this droplet is transferred from electrode to workpiece. This what I have already discussed in detail, what it's called you can say in my uh, some physics of welding lecture that you can observe. So here the Lorentz force which is generally responsible for metal transfer, that's Lorentz force generally generated due to the effect of current flow, and it's self-induced you can say electric field, that already you are very well familiar. So you can say once a current is flow through a conductor, Generally around the conductor, you observe that I have already discussed it very clearly. Some magnetic field is generated. This magnetic field generally in case of welding arc, you observe that there are two different types of force here is created. One is called axial force, another one is called radial force. I have already discussed that things also very clearly. If required, I can draw the figures and I can explain. But what happens, first of all, I'll discuss this thing without drawing the things. After that, if required, I'll just explain that things in figure also. So this radial force, whichever is coming due to this electromagnetic effect, that force is generally called Lorentz force. Generally, higher the Lorentz force, generally you can say higher is the chance of neck formation and higher is the chance of drop detachment, you can say. That's why always you should keep it in mind. If the what it's called current increase in case of a metal transfer, or you can say consumable types of electrode, keeping all other parameter constant, that means voltage, what it's called, welding speed, all other things are constant. If we increase the current, generally you always keep this thing in mind, your what it's called drop transfer rate is increased. That means per second you will get more number of drop. What I'm telling, understand? This is one case. And if you reduce the current, then opposite things, your Lorentz force, which is a 8 force, which generally responsible for neck formation, will reduce. So chances of formation of a droplet will be less. So your drop transfer rate also will reduce. On the other hand, in case of voltage, generally in case of voltage or welding voltage, always you should keep it in mind. Welding voltage, always you should, you are very well familiar. Voltage is what? Voltage is due to, you can say, due to this resistance in the arc region, that you can say. So what once voltage is increased, then what does it mean? Voltage is increased, then you can say resistance of the droplet also, you can say droplet formation also, one way you can say is increased. That way you can say. What I'm telling, understand? So in case of once your voltage is increased, then you can say your drop transfer rate also decrease. How it is? Little bit I will explain. Like in case of arc, generally how the voltage is varying, that you should know. Okay. Generally in case of arc, always you should keep it in mind. Arc voltage is equal to, I have already explained, A plus BL. That means you can say arc voltage is depends on arc length. That means if arc length is increased, then voltage, that means voltage is directly proportional to arc length, you can say. So if arc length increase, then you can say what it's called, your voltage, arc voltage increase. So if arc voltage increase, you can say your heat loss increase. So if your heat loss increase, then always you should keep it in mind. Your heat and the heat for required for formation of the droplet also decrease. So that means your drop formation chance also will decrease, that you can say, because less it is going to your, you can say, your droplet formation purpose. That's why what happens, if your arc voltage increase, that way you can say that your drop transfer rate will also decrease. So if I'll show these things by drawing, then it will be very clear to you. I'll just draw it, these things later on. So I think you got the idea. Always you should keep it in mind. In case of drop transfer, the effect of voltage is it's reduce the drop transfer rate, keeping all other parameter constant generally. And in case of the effect of what is called current, welding current, if you increase the current, your drop transfer rate will generally increase. These things you should keep it in mind. So R Palani, good afternoon. Palani, do you have any queries? If you have any queries, you can ask me. If you have any queries, you can ask me. Yeah. Then I'll just draw this figure, then it will be more clear to use related to what it's called metal transfer, drop transfer. So I'm sharing my screen. So here I am just going to draw the things, then it will be very clear to you. So you can see how the metal drop transfer is occurred. That related things now I am going to discuss little bit more clearly. So what I have told you, you have asked a question, sir. Would you please explain the effect of current and voltage in case of drop transfer? So I have already told you, if you draw the curve for effect of, you can say, let this is your, this y-axis represent your drop transfer, drop per second I am writing, and let this x-axis represent is your current. So always you should keep it in mind. Generally, with the increase of current, you can say your what it's called drop transfer also will increase. That means if current is more, you can say your drop transfer also is more. Keeping all other parameter constant. That means let us consider this is for a voltage V1. For a particular voltage, if you increase the current, then what happens? Your drop transfer will increase. Similarly, for another voltage, let us consider V2. If you just draw the drop transfer versus current for another voltage V2, you will observe that your drop transfer generally also will increase with increase of current. Now here always you should keep it in mind. Just you can see from this figure itself. So for a particular current, let us consider this I current. For this current, for a particular current, you can observe that with the variation of, for a particular current I, you can observe that with the variation of voltage, your drop transfer, also varied. Let's for I current, your in case of V2 voltage, you are getting a drop transfer. Let us consider D2, and for V1 voltage for I current, let us consider your drop transfer is D1. So here you can observe that here drop transfer D1 is greater than D2. D1 is greater than D2. But here one thing you should keep it in mind. Here you see V2, generally always you should keep V2 is less than V1. What I am telling, understand? That means lower the voltage. So what you can say, or you can say V1 is greater than V2. What I am telling, understand? So no, actually this is here is D1 is this. So D1 is this. So you're here just erasing this thing, that then it will be more clear to you. Just a minute. So here always you should keep it in mind that D1 is greater than D2. So but here always you should keep which whether V1 is more or V2 is more, that you should know. So here just I am just writing these things. So here always you should keep it in mind for V1 voltage. Whatever the D1 you are getting, so this V1 voltage should be less than V2. This you should keep it in mind. That means lower the voltage, you can say lower the voltage, higher the drop transfer rate, and higher the voltage, you can say higher the voltage, you will get lower number of drop transfer. This you should keep it in mind. But for increase of current, like from here to here, if you increase the current, you can observe for each and every case, keeping all other parameter constant, like for a particular voltage, your drop transfer generally is increased. This is the generally you can say curve for drop transfer rate with the variation of current and voltage. This you can say. Okay, this you should keep it in mind. So, is there any other questions? If you have any other questions, I will explain. 1 minute, let's see. Yeah. So Muhammad Usman. Good afternoon, Muhammad Usman. Do you have any queries? If you have any queries, you can directly ask or you can write it in text box. I will just reply your queries if you have any queries. Then Abhishek Jakkar also. Good afternoon. Very good afternoon, Abhishek. Do you have any queries? If you have any queries, you can ask me. Yeah. So last week itself, actually, one of the student asked related to some other queries that is related to, you can say, welding heat source efficiency and melting efficiency related thing. So he asked me, sir, what is the difference between heat source efficiency and what is called melting efficiency? If you can explain these things clearly, then it will be beneficial for them. So I have already discussed these things very clearly, what it's called in the physics of welding topics itself. So as you have asked this question again, I will explain this two different types of efficiency very clearly here. So it will be better. I will use what it's called this whiteboard. Then it will be more clear to you. So I am using this whiteboard. So, you know, all of you are very well familiar about this, what it's called efficiency, heat source efficiency, and you can say melting efficiency. So I am writing there are generally two types of efficiency we observe. One is called heat source efficiency. Another one is called melting efficiency. Correct? These things already is very well familiar to you. Then also little bit I am explaining. Heat source efficiency means, you can say here I am writing eta is heat source efficiency is equal to, you can write as nominal heat, that generally what happens, heat supply from, you can say heat supply from what you can say electrode to workpiece or from arc to workpiece. How much it is, that means here I am writing, then it will be more clear. So heat source efficiency means heat from arc to workpiece divided by nominal heat. Nominal heat from, you can say power source. Nominal heat supply from welding power source. Welding power source, I am writing PS. So this is the definition of heat source efficiency, you can say. Heat source efficiency means whatever the power source you are using for doing the welding. So from power source some heat you are supplying, but all the heat is not going to workpiece. Some heat is lost. You can say some heat is lost or lost in between your what it called power source to workpiece. That loss is due to different reason. That reason due to the what is called resistance of arc, due to convection, due to heat absorbed by some what it's called resistance of wire. Also it can be whatever the generally electric wire and other things we use, that also can absorb some heat. What I'm telling, understand? So for different reason there can be the loss of heat. All the heat is not absorbed by the workpiece. You are very well familiar. Or all the heat is not going to the workpiece. Whatever the heat you are supplying from the what is the power source, all the heat is not going to the workpiece. Some loss is taken place. So according to the definition of, you can say, um, efficiency, efficiency is output by input. So here you can say output is equal to your heat. Output means you want heat should go to workpiece. That means how much heat you are getting in workpiece, that is your output. And input is here generally, you can say, how much heat you are supplying from the power source. That is called nominal heat supply from welding powers. That way you can say. So generally you can write nominal heat supply from the you can say power source. You can write as, let us consider power source have a welding current and welding voltage you applied is welding current is, let us consider I, and voltage let us consider you apply is V. So V into I is known as, you can say, nominal power. Now with this what happens, what you need to apply with this, if you multiply time required to weld T weld, then you can get this power, means its unit is watt, this VI unit is watt. With this if we multiply time of weld, then this time if we multiply, that means second if we multiply, let us consider second if we multiply, then we can get the heat unit as joule. This mass of heat which is supplying from what is called power source, this mass of heat you are supplying. But due to some loss of heat, generally you are not getting all the heat here, correct? So that is generally called heat from arc to workpiece. Let us consider that heat is Q, that I don't know, that heat is in this, Q is in watt, W. With this if we multiply welding time, then we will get heat from arc to workpiece. What I'm telling, understand? Heat from arc to workpiece, that means this you can say W into second, watt into second, its unit will also be joule, correct? Now this way generally we used to calculate what it's called, we used to calculate, you can say, so T weld is common, so you can write Q by so what we were discussing, heat source efficiency. 1 minute. So you can observe that this Q is generally heat which is absorbed by the workpiece. What is Q? So here you can write Q is the heat absorbed by the workpiece. This is in watt. Always its unit is watt. Okay. So or you can say rate of heat. Rate of heat, Q is equal to rate of heat absorbed by work, or you can say heat power absorbed by the workpiece. And what is VI? VI is the heat supply by the workpiece. Now, how we can calculate this Q? I have already discussed these things in details. Generally, this Q you can measure with the help of calorimeter. I have explained this thing very clearly. You go through that lecture, that is in physics of welding, you will get the detailed idea. So generally what we used to do, first of all, there is, let us consider in this plate we are going to do the welding. So here let us, this is the electrode, with the electrode this is the arc. Generally below this workpiece we use the calorimeter. To know these things very clearly, I have explained the things. You go through the lecture, you will get the detailed idea. So here generally in this calorimeter we use generally a inlet water pipe, and there is a outlet water pipe. So this water generally it's flow through this calorimeter. This is generally calorimeter, and this calorimeter have generally two thermocouple. This is on thermocouple. Let us consider this is thermocouple. I am writing TC out, and this is here also on thermocouple inlet size also on thermocouple is there, that is called TC in. Let us consider I am writing. So this TC, by using this, once this arc generally do the welding, then this arc generally supply heat from this arc to workpiece, and workpiece to this you can say heat to workpiece to this water. So due to this heat supply from workpiece to water, this temperature of the water increase. This temperature of the water generally we measure with time. With time generally we measure. I have explained these things. By using that, there is some calculation is there, that is called generally, by using that calculation you can easily measure what is Q. Q generally is, you can write as integration of what is called rho C into temperature difference. That is called the density of water into C into dt, and its mass flow rate also is required to put. So with, by using this you can say here I am reading, instead of rho here I am writing mass flow rate, mf into C into dt. mf into C into dt. That means how much flow of water is there. Accordingly generally we measure the things, and if we just integrate these things over time, let us from a starting time 0 to for a particular time alpha. Okay, then what happens, you can easily measure the what is Q value. Why, what is C? C, you can say C is the specific heat of the water. You should keep it. What is dt? dt is the temperature difference, that means inlet temperature and outlet, because this water temperature is changing due to supply of heat from arc to workpiece. Due to that, generally whatever the dt you are getting, this dt generally you need to put. By this you can calculate this Q value. So with the, and V and I is known to you, that is the heat voltage and current supply from the power source. Okay, that is very well known to you. So by using this formula you can easily find out what is the heat source efficiency. This is called, you can say, heat source efficiency. I have already discussed this thing very clearly there. You go through these things, you will get. So this heat source efficiency generally is depends on type of weld machine as well as type of welding process also. Like you can observe that for submerged arc welding, this heat source efficiency is very high. Similarly, for laser welding process, general heat source efficiency is very less. Like in what is called, I have already given you the detailed idea about different types of heat source efficiency. Like in case of TIG welding, what is the heat source efficiency? In case of SMAW welding, what is the heat source efficiency? MIG welding, whatever the conventional different types of welding process are there. Most of the welding process details heat source efficiency generally I have provided there. And what is the reason behind this for variation of these different what is called heat source efficiency, that also I have explained very clearly. Because you may think that laser welding is such a welding process, it is a very high advanced welding process, its efficiency is very high. Not like that. Laser is such a welding process where the efficiency can vary from 5% to even 50 to 70%. What I'm telling, understand? 50 to 60%. It depends on actually surface condition, because laser power loss is very high because it depends on surface quality. Because laser welding is based on, you can say, light energy. Now the light is fully depends on its reflection types of phenomena, correct? If the surface is shiny type, then you can say due to reflection more heat loss will be taken place and less heat will be absorbed. What I'm telling, understand? So if we can increase the absorbability of this workpiece, then we can increase the laser what it's called heat source efficiency. That I have explained also. Now we need to explain another melting efficiency, another efficiency that is called melting efficiency. So what is melting efficiency? Melting efficiency, let's eta m I am writing. I have already discussed these things also very clearly in my what it's called lectures. So instead of writing all these things here, it will be better to show you that things, then it will be more clear to you. In between also, if you have any queries, you can ask me question. Yeah, someone asked me some question. Yes. So I am just, yeah. Vikas Chanda, good afternoon. Week 2 assignment question number 10 has two correct option, that is option A and option B, but a student who opted option A has not awarded marks. I told management many times. Yeah, Vikas, we will take care of this thing. I am not noting it down. Definitely will get the marks if it is correct. Can you please explain the question? Then definitely I will just uh, tell the correct option also. Okay, definitely will get the marks. In assignment week 2, I am writing these things. Week 2 assignment question number 10. U10. Yes, you will get the marks. I'm sure. I am will provide you what it's called. If it is correct, we will provide you marks. Okay, you need not to worry about this thing, because today itself I will inform the management as well as my tutor, not tutor actually, who is the teaching assistant is there. I will just inform him and he will correct it today itself. Option A and B are correct. Option A and B are correct, but student who opted option A has not awarded marks. Okay, okay, I'll see. A and B are correct. Now itself I will do this thing. So if you'll face any such problem, directly you can contact with me by mailing. I am sending my official mail ID here itself also. Okay, my official mail ID is you can say pankaj.biswas. If you want, you can write also at the rate of iitg.ac.in. So in this official ID, you can send me mail. If you will face any problem, definitely I'll clarify it and I'll give the if required, I will just correct the things as well as I'll provide the marks if required. Okay, definitely I'll provide. You need not to worry about this thing. You will get marks if your option is correct, and I'll check that assignment to question number 10. Definitely will get it, because this question generally has been provided by my TA. So definitely we'll check it. I'll check it carefully and I'll definitely provide you marks. You need not to worry about this thing. If you have any queries, you can ask me. So I am just discussing little bit what it's called melting efficiency here. So melting efficiency, you can see here I have already written like melting efficiency, you can say, you know that during welding process, whatever the heat is supplying to workpiece, all the heat generally are not required to, you can say, do the welding, you can say, because what happens in fusion welding process, you can say the heat which is actually required to do the welding is just to melt the workpiece and solidify, that types of things, you can say. But here from the arc, whatever the heat you are supplying, or that all the heat are not utilizing, or all the heat, you can say, are not required to do the welding, correct? Because you know, for melting purpose, you can say, for melting of the base material as well as filler material, let us consider its temperature, melting temperature, it's, let us consider 1500 or 1400 degrees centigrade. But all the 1400, because to raise a 1400 degree centigrade temperature of filler wire as well as base material, whatever the heat you are providing, let us consider by using that, you are getting a temperature in filler wire as well as base material is 2000 degree centigrade or 2500 degree centigrade, like this. Let's see 25, because but your heat require is to raise a temperature which is 1400 degree centigrade temperature. But whatever the heat you are supplying to workpiece, that raising a temperature which is much higher. That means it is at 2500 degrees. That means 1000 degree more temperature you are supplying, or you can say you are supplying such a high heat. So your temperature rising around 1000 degree more centigrade temperature. What I'm telling, understand? So that is actually not required. That's why melting efficiency tells. That means whatever the heat actually require to melt the material divided by whatever the heat you are supplying to workpiece, whatever the heat you are getting to workpiece. That means you can say whatever the heat you are getting to workpiece, that is the output of what? Heat source efficiency. So from heat source efficiency, whatever the heat generally you can get from, you can say you can get from heat source to workpiece, that heat here is a input. What I am telling, understand? That heat is the input of that thing, and here the output is, here you can say it, here I have shown, here I am sharing these things, you can see these things also. Just here I am showing this thing, then it will be very clear to you. Lord, 1 minute. Little bit here. These things I will just explain in the, what it's called, whiteboard, then it will be more clear to you. So what I have written here, you can see, melting efficiency, here I am writing, is equal to, you can say, heat required to melt the filler plus, what is a plus, current material, base material. Just heat required to melt the filler material plus bed material, you can write, divided by heat absorbed by the workpiece, by the workpiece. That means here you can write little bit for your convenient. Here I am writing this, you need not to write, just you can say, here you can say, let us consider the melting point of filler material as well as base material, let us consider 1400 degrees centigrade. So here you can write heat for 1400 degrees centigrade temperature, but here let us consider whatever the heat is absorbed by the workpiece, that heat generally let us consider heat for, let us consider your maximum temperature you are getting due to this heat supply, let us consider 2000 degrees centigrade temperature. What I am telling, understand? Just for example I am just showing. So here you see whatever the heat is absorbing by the workpiece, all the heat is not, you can say all the heat is not required to melt the workpiece, correct? That's why it is called melting efficiency. Means melting efficiency means to melt how much heat is required. Generally that is called melting heat. But actually you are supplying more heat from, you can say, arc to workpiece, correct? That much of heat is not required to melt that things. That's why I have written like this. Okay. So here generally heat absorbed by the workpiece, this you can get from the heat source efficiency eta is. I have already told you. So what is eta is? I have already told you eta is equal to Q divided by V into voltage into current. So here this Q is called heat absorbed by the workpiece. Q is called heat absorbed by the workpiece. So Q you can write as eta is into V into I, correct? V into I. So this Q things will be actually, you can see in case of heat source efficiency, this Q was as a output, but in case of melting efficiency, this Q is act as a input here. What I am telling, understand? This you should keep it in mind. And so here you can write heat required to melt the filler wire as well as base material divided by this Q value, whatever the heat supplied to the workpiece. Now, how you can calculate this heat required to melt the filler plus base material? How you can calculate this thing? That things I am little bit going to explain. Before going to explain this thing, let us see if you have any other queries or not. No other queries are there. If you have any queries, you can ask. Abhishek, you have any queries? In between also, if you have any queries, I will definitely discuss here. But because you need not to send the same message again and again, we'll definitely take care of this thing. Right? You need not to worry about these things. We will give you marks if it is correct. This you just should keep it in mind. Okay. You need not to worry about this. Okay. Today itself, I will just take the action for this. I was not ever these things, but I have already told you my what it's called. Because you need not to send me the same message again and again. Why? We will resolve this issue. Okay. If anyone has any other queries, they can ask me. So you see, I was discussing about what is called melting efficiency. So melting efficiency, how we can calculate. So for calculating melting efficiency, let us consider after welding, you got a weld bit which looks like this. So in this welding, let us consider this is your, you can say, let us consider this mass is your filler material, and let us consider this is your what is called base material, which is subjected to fusion, that means melt, which is subjected to melt. So let us consider this hashed line I am representing as filler wire, and this you can this total cross sectional, this fusion zone, this total fusion zone you can get by optical microscope itself, and this total cross sectional area also you can easily calculate with the help of that microscope, some optical microscope or some what is called high resolution cameras are there. By using that things itself, you can easily measure what are the cross sectional area of this fusion zone. You can easily get. Fusion zone means which is subjected to melting. So let us consider here I am writing cross sectional area of filler wire is AF and cross sectional of base material is AB. So here you can say total area AT is equal to, we can write as AF plus AB. Now you actually don't know what is the value of AF and what is the value of AB. This you don't know exactly. This you need to calculate, but you can easily calculate what is AT, because AT is the just fusion zone which you can easily observe from optical microscope or otherwise high resolution camera. By this you can easily calculate these things and you can easily predict that thing. Okay. Now, so AT is known, you can say AT is known, but AF and AB is unknown to you. AF and AB is required. What I'm telling, understand? AF is called filler material. This filler material you can easily calculate. AF also you can easily calculate. So AF also is known, you can say. But this base material area you can calculate how? You can calculate how? By difference. That means you can say here AF and AT is known to you. So you can write your AB is equal to your A total area minus A filler area. How to calculate AF and A total area, cross sectional area AT, that I will explain very clear way. What I am telling, understand? So generally here I am writing that things. So heat required to melt the filler wire, how you can calculate? So heat required to melt the filler wire, you can write like this. Like let us consider a filler wire. How much volume of filler wire is generally depositing per second, that I am going to calculate. So AF, if I know AF, so AF into what? Velocity of weld. AF into velocity of weld. Here I am writing AF into V, velocity instead of V, here I am writing W, that will be better. Welding speed, W. AF into V, this will give you what? Rate of, means mass flow rate of filler wire. Okay, this is the mass of filler wire per second. How it is coming? Because AF unit is, let us consider meter square, and welding speed unit is meter per second. So here what are the things you are getting? Meter square into M, correct? Meter square into M divided by the, so meter cube by S. With this, if we multiply, so this is, you can say volume flow rate, that also you can say volume flow, because rho will be constant. Okay. So AF into W, with this if you multiply A's filler material. What is A's filler material? A's filler material is the heat required to raise a temperature of its melting point and melt it. That means ASF is what? How much heat is required to heat unit volume of material and to melt it. That way you can say. That is called ASF. What I am telling, understand? So this will give you a, so what is the sound? This is the heat for, this is the, you can say this is the heat for, this is the heat for welding. This is the heat for, heat required to melt the filler wire. That way you can write, correct? And another things is plus with this T weld also will be there. With this T weld also will be there. If we apply T weld, then it will be joule. Just if we'll just here it will be T weld also will be there. Okay. If we apply T weld, then T weld will be there. So here also if we apply QE into T weld, here also T weld also will be there. This you should keep it in mind. Okay. But if you just consider that power only, then T weld will not be there. Okay. Similarly, plus whatever the base material cross sectional is there, that is the base material into velocity of welding. This will give you what? This will give you the volume of base material which is melting. Volume of base material which is melting. So with this, if we multiply HB, what is HB? HB is the, you can say, heat required to melt unit volume. Whatever the heat required to melt unit volume of base material. This you should keep it in mind. Okay. So this will give you, this will give you total heat required to what it's called melt the base material per second also you can say. Okay. With this, if we multiply T weld, then you will get it in terms of joule. Similarly, here also Q into T weld will be there. Now you see T weld is total weld time. So top side T weld is there, bottom side T weld also is there. So what are the things here you are getting? AF into W into HF plus AB into W into HB divided by you can say Q. So what is Q? Q is equal to eta heat source efficiency into voltage into current. Now you see, you know what is HF? HF I have already told you. HF is equal to, I have already told you, rate of you can say heat required to melt, you can say rate of heat required to raise up to melting point temperature, up to melting point temperature of filler wire and melt it. Whatever the heat is required, that means HF equal to rate of heat required to raise up to melting point temperature of filler wire of you can say unit volume of material, unit here instead of writing of unit volume, here you can write of unit volume of filler wire, or here also you can say of unit volume of filler wire of filler wire. This you should keep it in mind. Similarly, HB is what? HB is rate of heat required to raise up to melting point temperature of unit volume of base material. What I am telling, understand? This you should keep it in mind. So here you see, so you can see, so HF, what is the unit of HF? HF unit you can write as, HF unit you can write as watt per, you can write as watt per meter cube. Watt per meter cube, correct? This you should keep it in. What is the unit of this thing? Watt per meter cube. With this, so HF unit is watt per meter cube. With this, if you multiply, so you can see, so in next slide I am just showing watt per meter cube is there. So HF unit I have already told you, its unit is watt per meter cube. That means for melting, to melt the what is filler material. Okay. Now with this, I have already written IHF into AF into velocity of welding omega. What is the things here you are getting? So HF is watt per meter cube. Cross sectional areas unit is meter square. Welding voltage unit is meter per second. What are the unit here you are getting? Meter cube cancel out top side. So here you are getting watt per second. So watt per second is its unit is what? Joule. What I am telling, understand? So watt per second its unit is coming as joule. So with this actually if you multiply T weld, you will get generally what it's called. So what is the things? No, actually it is not well. Watt per meter cube, 1 minute. Yes, it's okay. Okay. So you are getting is in terms of joule, correct? How it is coming? You got the things. Unit things. What are the things you are getting? I have already explained this thing. Rate of heat required to raise up to melting point temperature and melt it. Watt per meter cube. Here you see. So watt per meter cube, here also meter cube per second is coming. Actually this is actually heat, na? This is not watt per meter cube. This is actually joule per meter cube. Sorry. This is actually joule per meter cube. This is actually joule per meter. So this will be actually what? Joule per second. This will be actually joule per second. This will be actually watt. Unit is watt. Okay. Just here these things. This HF has a unit that is called joule per meter cube, because I have already written here. Heat required, actually instead of rate of heat, it is actually heat required to raise up to melting point temperature of filler wire and melt it. If you use rate of heat, then T weld terms will not come. Okay, this is the thing. Both other things is okay. Okay. Now by using this, so here you are getting what are the things? So top side generally melting efficiency. What are the things here you are getting? AF into welding speed into HF plus AB into welding speed into HB divided by, you can say, Q. Q is what? I have already explained these things very clearly. Q is the, you can say, eta heat source efficiency into voltage into current. Okay, this thing also I have explained. Now I have already told you that this total cross sectional area you can easily calculate from optical microscope. After means doing welding, you take the cross section, and you from this cross section view, we can easily find out what is the total cross sectional area of the weld, or total cross sectional area of the fusion zone. It is, you can say, total cross sectional area of fusion zone. Fusion zone. These things is very well known to you. Now, how to calculate what it's called AF and AB? So AF generally we can calculate with the help of, you see, AF is what? AF generally how much filler material, generally, you are supplying from the what is called spool per unit time. First of all, that things you are calculating. For that unit times, how much length of weld material you are getting. Okay, based on that thing, generally you can calculate these things. So let us see. This is the arc. This is the arc. Okay. So this arc generally is subjected to some wire feeder mechanism. You can say from there generally droplet is forming and it's transferring. So you see this wire feeder have a, so you can say this whatever the arc is there, this arc is melting this consumable electrode, and this electrode melting and it depositing. And once it depositing, generally by this wire feeding mechanism, you generally continuously supply the what is called electrode, or you can say filler wire. Correct. So let us consider here the filler wire have a speed is WF. So here I am writing WF is the filler wire speed. Okay. So filler wire, let us consider this filler wire have a diameter is, or radius is, let us consider R. So per second, how much volume of material will be deposited, that you can easily find out. That is actually your cross sectional area pi r square into velocity of filler wire. This is the volume of filler wire per second is melting. This volume of filler wire generally is equal to what? Your cross sectional area of filler wire into velocity of weld. So velocity of weld I have already represented as W, and here WF, always you should keep WF is feed speed, feed rate of filler wire. This is the feed rate. That means how much speed generally is there per second, you can say per second of this filler wire, whatever the filler wire is there. Okay. So from here, so you know the cross sectional area of this filler wire, you know this feed is feed, you know this welding is feed. So you can easily find out what is AF. AF is equal to what? AF is equal to, you can say, pi r square into speed of wire, or you can say feed rate of wire, feed speed of wire divided by, you can say, your welding speed, your welding speed W. So W is what? Welding speed. Welding speed, or you can say welding transverse speed, traverse speed. That means per unit times how much length of welding you are doing. That is called welding speed. Okay, this you should keep it in mind. So all the things is known. WF is known, welding speed is known, R radius of the what is called flare wire is known. By using easily, you can easily find out what is your AF value. So if you know this AF value, then you can easily find out what is your AB value. So AT, total cross sectional area, you are getting from what it's called optical microscope after taking the cross sectional view of weld bit geometry after welding, correct? So this total cross sectional area is equal to your flare wire plus base material. So AF now is known to you, AT is now known to you. So what will be your AB value? So AB you can easily find out, that is your AT minus AF. Now I think it is very clear to you. So you now know everything. So AF is known, AB is known, welding speed is known, A is F is also known, A is B also known. What I am telling, understand? So all the things is known to you. Okay, so you can easily find out, if you know this, what is called heat source efficiency, if you know this welding voltage, welding current, so you can easily find out what is the melting efficiency. What I'm telling, understand? So this way generally you need to calculate melting efficiency. So rest of the things already I have explained. Do you have any other queries? If you have any other queries, you can ask me. No further queries are there. If you have any queries, you can ask me, because you will get the marks. Today itself, I will just discuss with my TA. They will provide you the marks, right? You need not worry about this. I think time is also off. If you have any queries, any questions, you can ask me. Actually, this 2 question is asked by one student who called me and who told, sir, if you can discuss these things in little detail in live session, that also will be helpful. So that's why I am discussing this thing today here. Okay. If you have any further queries, you can ask me. Now also I am in live. If you have any queries, you can ask me. But I think time is up. Yes, there are no further queries. So I think we can close here. We can stop our live session. So Rekha, hello. Okay, I think it will be better to close now, because no further queries are there. So it is better to close. Thank you. Okay, thank you.